All right, so let's continue to take a look at this vector that's the derivative of our unit tangent with respect to arc length. And so for that vector, we know that the curvature is going to be the norm of that vector, and so we can actually write dt ds as the curvature times some unit vector n. Okay, and this unit vector n we will call the unit normal vector. Okay, so kind of remembering that dt, so the derivative of the unit tangent with respect to an arbitrary parameter t, is really just ds dt dt ds. And our curvature is really the norm of this dt ds. And so dt dt is really going to be ds dt times the curvature times our unit normal vector. And so kind of if we take that unit normal vector, so that's the arc length, that's the norm of the derivative of the unit tangent vector. So what was that with respect to s? Well, it was 1 over ds dt times the derivative with respect to our arbitrary parameter. And so what happens, these ds dt's cancel out, and this is really nothing more than the derivative of the unit tangent with respect to our arbitrary parameter, the norm of that, times our unit normal vector. Now what that gives us then is an expression for the unit normal in terms of an arbitrary parameter t that we happen to be using. So if we take a curve, we take the derivative of it, we normalize that, so we get the unit tangent, then we take the derivative of that expression, normalize that, and now we're back to our unit normal vector. And so what we're also able to do is kind of take this even further back to the original parameterization. What's that going to look like? That t is going to be just what we said, the derivative of our original vector divided by the norm of that. And so here we're kind of going back to the physics notation where we're saying that if we're putting a dot above it, we're really saying that that's going to be the derivative with respect to our parameter t. 2 dots mean the second derivative, and so on and so on. And so if we then take the derivative of this expression with respect to t, then we get our 1 over the norm of the derivative of the first derivative times the second derivative plus, so what is this really? It's nothing more than our product rule. So here we've got the first times the derivative of the second plus the second times the derivative of the first. Now what is this derivative of the first that we're talking about? That thing is really just, so if we take the derivative of 1 over that, we get a negative 1 over the original function, so the derivative of the outside function, keep the inside the same, times the derivative of the inside function. Now that derivative of the inside function we can write as the square root of the dot product. And so now again we take the derivative of the outside function, keep the inside the same, times the derivative of the inside function. Well, the derivative of the inside function is really then just a product rule. So we've got 1 over 2 times the norm of the first derivative times the second derivative dotted with the first function plus the first function dotted with the second derivative. And so kind of putting those two together, these two are really the same because dot product is independent of order. So that gives us 2 of those. Our 2's cancel, and we end up with the first derivative dotted with the second derivative for the numerator and the norm of the first derivative in the denominator. Okay. Now we're going to switch notation a little bit so we don't have so many dots kind of running around all over the place. Then another common notation for dot products is this kind of bracket notation. So we've got, this is really what we'll call inner product notation. And so it kind of signifies the same thing that we're talking about for the dots. And so when this shows up in the notation, then we're not getting quite so confused with we got dots above, we got dots on the side, and so on and so on. So coming back to put all of this together, we get the derivative of the unit tangent vector with respect to our arbitrary parameter. Just looks like the second derivative divided by the norm of the first derivative minus the inner product, so the dot product of the first and second derivatives divided by the norm of the first derivative cubed times the first derivative. And so this kind of gives us, if we're just given a curve, rather than kind of jumping through this big process of normalizing it and coming back and then taking the derivative of that, and we can just do it straight to in terms of the in terms of the original parameterization that we were given for the curve. So this is kind of a handy formula to have. Now if we want the unit normal, we just, once we construct this, we normalize it, and we have our unit normal vector. So now let's kind of go over to GeoGebra and take a look and see what this looks like. Kind of graphically, we can kind of put all three, or put these two things together and kind of see really what's going on. Alright, so let's take a look at GeoGebra and see if we can kind of get some intuition for what these unit normal vectors are and how they're related to our tangent vectors. So let's say that we are, let's just create a parametric curve in our 2 dimensions. So let's say that we've got a curve C, and we'll say that that one's going to be a curve. Let's kind of make it a little exotic. How about sine of 2t times cosine of t and sine of 2t times sine of t, with t going from 0 to 2 pi. Okay, so we get our 4-leaf rows out of that one. Let's kind of move that over, zoom in a little bit so that we can kind of see what's going on there. All right, so there's our vector that we have. And so now, probably a couple of things that will go along with this, since we'll be interested in kind of the first derivatives and the second derivatives. I'm going to go ahead and compute those, but I'm going to hide them kind of in the background. And so if we wanted to compute those, let's say if we wanted, say, the first derivative, let's say that's dc is going to be the derivative of our curve C. So we'll kind of put that one in there. So at each point in there, it kind of computes the vector for that one. And then let's compute our second derivative. We're not really interested in what that looks like, but it's kind of cool anyway. Let's say that our second derivative, so ddc for our second derivative is going to be the derivative of our curve C, but now we want to make it the second derivative for what that one will look like. And so that one gives us a derivative. And so again, we're not really interested so much in what that curve looks like, but what we're going to kind of do with those things now. All right, so let's come up with some point on this curve. So let's make a slider that will be our angle. Let's say this slider T, and this thing is going to go from 0 up to 2 pi. Let's take it step 0.1. The animation, we'll just increase it 1 time at speed 1. All right, so now, if we're talking about a particular point on that curve, let's say that our point P is going to be our value C of t. So that's going to be our vector that's pointing to our point on the curve. And so as we kind of move our slider around a little bit, we can see that we're kind of tracing that around and going to different points on our curve as we kind of trace this thing around between 0 and 2 pi. Okay, so we've got that. All right, now what about our unit tangent vector? Okay, well, for our unit tangent vector, that was just going to be, say, t being the unit vector for the vector dc evaluated at time t, so that we have that one. Okay, so that gives us our unit vector. Let's change where that thing is actually positioned. So we say we want that thing to start at our point P that we have in here, and just so that we can tell the color apart, let's make it blue. And so now does that get us where we want to be? So for our unit tangent vector t, it's at our point t. It's always the same length, and as we trace it around through that curve, it's always going to be tangent to our curve no matter where we're at. And so that, sure enough, gives us our unit vector, unit tangent vector t. Okay, and let's say that we don't need the label on that one, and we don't need our label on our point P. So we know what that is. We've got our unit tangent vector, and then we've got so now, what about our unit normal vector? Okay, so for our unit normal vector, that one, we want to kind of do this one in terms of our original parameters t, original parameterization t, and for our original parameter curve there. And so kind of if you go back through the video just a little bit, you see the formula that we come up with. But what that one was going to be was, now this one was going to be our vector, let's see, do I need to, n being this vector that was our second derivative. So our second derivative, that was ddc of evaluated at our parameter t. Now it was divided by the length of our first derivative. So that's the length of our dc, also evaluated at t. Okay, so that was our first component. And then plus, our parameters are going crazy. Oops. Let's go back there. And so now what the rest of it was, we had that one, and then minus, we had our dot product. And so in GeoGebra, that is just our dot product of our first derivative and our second derivative. So that was dc evaluated at t and ddc evaluated at t. So that was our dot product divided by the length of the first derivative, dc at t, and that was raised to the third power, and this was going to be times our first derivative, dc evaluated at t. Okay, so that gave us our vector n, and let's see, so that one's showing up. Let's say that one's going to be their color n. But this thing wasn't necessarily a unit vector, so let's kind of go back and make that thing a unit vector. So that was our original derivative, so let's say we need a unit vector of that one all the way there, close that one in parentheses, so we put that one in there, and now yes, we do have our unit vector. Now let's again make sure that this thing is also positioned at our point. So where was our position there? We don't want it at the origin, we wanted it at our point P, so that everything is kind of there together. And so now what we have, taking these things back just a little bit to our point there, so our position 1. So what we've got now is our unit tangent vector as the blue vector, and we've got our unit normal vector as being, we're going to turn that label back on, our unit normal vector being our vector n, so that's going to be perpendicular to our unit tangent vector if we kind of measure what that one is going to be. So from there to there, we sure enough, we end up with an angle that is 90 degrees on that one. So we get a 90-degree angle between our unit tangent and our unit normal vector. Our unit normal vectors pointing kind of into the curve, and then we've got our, all of this is attached to our position vector. And so what we have now is kind of this two-dimensional coordinate system that kind of flows along with our curve as we kind of increase our parameterization. So we'll just kind of watch that as it goes around one time. That animation on. So as we slide it around, Sure enough, we get this coordinate system that kind of rotates relative to our fixed coordinate system, but on the curve, it's just kind of staying this perpendicular. One of them is in the direction of motion, and one of them is kind of perpendicular to that direction of motion. And so that really gives us what our unit normal vector is, what our unit tangent vector is. And so we only have one more vector to talk about to kind of go along with these things whenever we bump things up into 3 dimensions, and that's our binormal vector. So stay tuned for those, and I will see you guys shortly.